Okay, so let's look at our matrix equation once more. We have X, which is simply each row is a set of features for a data point. The value is y sub I for each data point, which is in this m by 1 column vector y. And we want to try to find f such that x times f is almost y. I'm going to use bold y and bold f to indicate that they're vectors. A small mistake, I had used bold y here. It actually should be unbold y, and that was a typo. Apologize for that. Let's go on though. We want to find f that approximately matches this equation. And we're going to do that by minimizing the difference between x transposed f and yi for each of these data points by taking the sum of the squares. That's what we decided earlier. And if we write the sum of squares in matrix form, it turns out to be simply the difference between xf and y transposed and multiplied by itself. So essentially it's the norm or the sum of squares of this difference vector, which is exactly what we have here. This quantity needs to be minimized. Now, to minimize a quantity, if you go back to high school, you need to make its derivative 0. But derivative with respect to what? The unknown quantity is f. In this case, it's a vector, so it's a bit more complicated than high school. You want to take the derivative with respect to every element of f. Well, if you studied vector calculus, it's fairly easy to do that. We won't go through that here, but just think about f as being one variable for the time being. The way you would take the derivative is you would expand this out, and you'd get one term which is f transposed x transposed xf. So there are two f's there. So when you take the derivative of that, you'll get twice x transpose xf, and then you'll get two elements where there's a y transposed x into f, or an f transposed x transposed into y. And for each of those, you'll get a y transposed x. So if you set the derivative to 0, you'll get twice of this being 0, which is essentially this minus this being 0, which are called the normal equations. X transposed f times f should be equal to x transposed y. Now x transposed f, if you look at it in matrix form, it's actually no longer a very large matrix. It's only an n by n matrix, because you took this long matrix multiplied by its transposed, you'll get an n by n matrix. You have f, which is a vector of length n, and x transpose y again will become a much smaller column vector. And so this system of equations is n by n, and this side is n, so you should be able to solve it exactly, as long as, of course, the matrix is not singular, or it actually has a unique solution. Most of the time it does have a unique solution, and so we solve this to get our f. Once we have our f, our least squares estimate for f is nothing but x transposed f, or x prime transposed f, where x prime is x comma 1. So given an x, the value of y, most likely by least squares, is x comma 1 transposed f. And that's our least squares estimate. Let's do an example. Let's take a simple 4 data point example with only one feature. So x is just a one variable. X can be many variables, of course. And y is a set of values as well. We solve the normal equations. The normal equations will look something like this. If you take x transpose x, each element of x is x comma 1. Y is just the values of y. The f that you get by solving the normal equations turns out to be this one. And when you plot f transpose x, which is simply the line 0.11x minus 0.26 on a graph, and you have the xy coordinates being plotted as well, x comma y, you see that the line actually almost fits the data. This is all that there is in linear regression. Of course, if there are many variables, you'll have possibly many such plots, one for each value of each feature x, and the f will be much longer in terms of the number of coefficients. So we have a approximation for y for every value of x that we might come across. But we also might want to ask, how good is this fit to the data? A common measure of how good the fit is called the R-squared value, which is simply the sum of squares of the errors of our actual estimate. So you have f of x, which is f transpose x of I for each data point, minus the actual value. You square it and sum, and you'll divide that by the variation in y about its mean. So y has a certain mean, which could be somewhere here, and you want to see how the error, the sum of all these errors, compares with the actual variation in the y values across their mean. Doesn't sound like a great measure, because if you have a steeper slope, you'll probably have a higher value over here. But then, if you have a steeper slope, you're actually tolerating more error in your estimate. But this is a common and easy to calculate measure. There are better measures which tell you how good each of these coefficients are in terms of how confident one should be in each coefficient, but we won't go into that in detail. For this particular example, the data is pretty much fitting a line. The R-square value comes out to be somewhere around 0.95. As you can see, the R-squared value can be close to 1, in which if there's a good fit, and can be close to 0 if there isn't a good fit. Let's take another example. This is an example which is a little bit more realistic. It comes from a book called Super Crunchers, written by Ian Arias in 2007, which talks about the power of reasoning from data. It's a great book if you want to read it. He tells the story of a wine expert called Orly Ashenfelter, who predicted the quality of wine based on the winter rainfall, the average temperature, and the harvest rainfall in a season. So Ashenfelter could predict how good a particular wine would be depending on the weather in the growing region for that wine, and do this much before the wine hit the market. And it turns out that his estimates were simply based on linear regression and turned out to be extremely successful, and surprised many experienced wine critics who would have to taste the wine many times and judge it before predicting whether it be a high-priced wine or not. The kind of estimate he got was something like, a linear least squares fit, which is, the F0, the F1, the F2, and the F3, and he got a very nice fit. The important thing to note is that we have possibly positive correlations between the output variable y and the input variables, such as a positive value here, here, and here, or we could have negative correlations. So in this case, 0.26 is negative, 0.0038 is negative. So if harvest rainfall goes higher, the quality goes down, unlike the positive correlation with respect to, say, winter rainfall. Let's take a look at a few more examples of correlation that one might get with a single variable. Of course, all this applies to multiple variables. You can always draw graphs of the value with respect to any of the feature variables. This is clearly very strong correlations. You'll get a very high R-squared value for if the data looks like this. Of course, if it looks a bit more scattered, you'll get a lower value of R-squared. And similarly, if it's negatively correlated, your slopes will be negative, which could have lower r-squareds if they're more scattered. And suppose your data is like this. Well, it doesn't look like there's any correlation, and the r-squared will reflect, because if you look at the variation of y across its mean, it's fairly large, and whatever line one puts around it, the variation of the y's with respect to whatever line one decides to draw will also be very large, and so this ratio will be close to 1, and r-squared will be close to 0. However, let's look at this case, for example. This is a little bit more subtle. Y is almost constant as x varies. So there's a line which goes through these points, but what's the r-squared value? Y doesn't change at all, and the line, if you fit it, might be exact or very close to being exact, so the error may be very small as well. So this ratio is again very close to 1, and the r-squared value is very small. So essentially you're saying there is no correlation. And that's actually true, because whatever be the value of x, y doesn't change. So the only way you can get non-correlation is not just if the data is scattered all across, but even if it's a straight line here, if y doesn't change with respect to x, then there's no correlation either. And lastly, we have another situation which we'll come to in the next segment, which is a situation like this. Whatever line one draws through these points, one will always make a lot of error. This is an example of nonlinear correlation. The data is correlated, so if you were to draw a line which is like a parabola, it would certainly work, but it doesn't work for linear correlation. For this and many other reasons, as we'll come to in the next segment, we have to go beyond linear least squares to more complicated prediction models.